Hello everyone, welcome to the Material Science class, MIG 300. This is the chapter 3. In this video, I'm going to start chapter 3, which is a new chapter for this course. Over the last videos, we have discussed the chapter 2. In chapter 2, we discussed the structure of the atom, and we discussed the different types of forces that would be located at the atomic scale. In addition, we discussed how the material properties in general could be related or dependent on these different types of forces, or in other words, how these forces would affect the different properties of material. This is what we discussed over chapter 2. In this chapter 3, we are going to discuss the structure of crystalline solids. Crystalline solid, it is one of the type of solid material. This means that there are different types of solids, or we can do classification of solid materials based on their crystal structure or based on their microstructure or atomic structure. One of these types of solids are known as crystalline solid, and this is going to be clear through this video. So the objective again over this chapter is just to discuss this structure, especially the atomic structure of these different types of crystalline solid. This is the main focus of this chapter 3. Why this chapter is important? Because of so many things. This chapter is going to be the basis for the next coming chapter, especially chapter 4, 5, and chapter 7. So it is highly important to understand these things that and information that we are going to cover through these videos that will be covering the chapter 3. Make sense? Another importance of this chapter and how it would be related to the entire course or subject of material science. As we mentioned, that the objective of material science is to teach you, or is to know the relation between the material properties and their structure. We have discussed the atomic structure in chapter 3 and chapter 2, or in other words, to be more accurate, we discussed the forces that located at the atomic scale and how they are related to the material properties. Here, we're going to discuss the atomic structure of this type of solids, which is crystalline material, and how these different structures would be related to the material properties. This will be covered in chapter 3. And again, the importance of this chapter is located that it will be the basis for chapter 4, 5, and 7 that shall be covered in the next weeks. Make sense? So, the first thing that we should distinguish or understand here is to distinguish the difference between crystalline material and amorphous material. Since the title of this chapter it is crystalline solid, so we should understand what does it mean a crystalline material in general, whatever it is, solid or liquid, but the focus again is going to be over solids. So what is the difference between a crystalline material and a non-crystalline material, or a material which cannot be classified as crystalline material, which commonly known as amorphous material? So we do have, in terms of the structure or in terms of the arrangement of atoms inside the material structure, we can group materials in general into two main groups. Materials known as crystalline materials and some other group of material which are amorphous material. A crystalline material is the one, as written here in the definition, is the one in which atoms are arranged. So this is the key condition, that atoms, they should have arrangement, a specific arrangement to say that we do have a crystalline material. So atoms should be arranged in a periodic, three-dimensional pattern. So I'm just going to stand for a while about periodic pattern. Forget about the three-dimensional thing for now. What does it mean pattern? What does it mean periodic pattern? Pattern is something that has a shape. If we're going to talk about the atomic structure, it means that to have a pattern inside the material atomic structure, you should have a group of atoms that form a certain shape. This shape is going to be known as pattern. Going back to chapter 1, we said that the material, if we're going to look at it through the microscope, there are different levels of the material microstructure or the material structure. We do have the microstructure, which is going to be at the atomic microscale. We do have atomic structure that we have to go deeply inside one single grain of the material crystal to see what's inside this material in terms of atoms. Here we are talking about the atomic structure. We can see the atom. We said that any material, it is a composition of set of atoms. So many atoms are combined together with one of the bonding forces that we cover in chapter 2 to form a material, right? So here, focus on the atomic structure. The focus is on the atomic structure, how these atoms are arranged. Here we are discussing the arrangement of this atom, not what type of force that is going to generate between this atom. The type of force, this had been covered in chapter 2. Here we are focusing on the arrangement, how we distribute these atoms inside the material. So we do have different ways. For example, if we consider these three examples of the material, forget about the title here, crystalline, polycrystalline, or amorphous. But as you can see, all of these circles indicate, or sphere indicate atoms. So this is one atom, this is another atom, and so on. So, but what makes this arrangement is different than this one, for example. This arrangement 1 and arrangement 3. You're still dealing with the same atom, right? But this atom, the atoms here, they do have a specific arrangement. They are well organized to form a certain pattern. And I'm going to define what does it mean pattern in detail. But here, atoms are very random. So we do have a well-defined arrangement of atom for this type of material. But this other type of material, it has a random distribution of the atoms inside its structure. Despite we could have the same atom type, you may have, for example, this atom, it will be aluminum. For example, like this is aluminum material and this is another aluminum material. But this, what makes this aluminum material is different than this one. Atoms here are well defined with well-defined arrangement, but atoms here are randomly distributed inside the material. This is what distinguishes crystalline from amorphous. So the talk here is not on the type of the atom, is not on the forces between atoms. The talk is about the arrangement, how we distribute, how we do arrange these atoms inside the material. This is the objective of this chapter. As we discussed before, any property of the material is related to all the things that are happening at the atomic scale. In chapter 2, we knew how the forces affecting the material properties. Ionic force, it gives properties covalent that is different than covalent bond or metallic bond. So the forces, they do affect the material properties. The arrangement of atom itself, it do affect the material properties, and this is the objective through this chapter, is just to understand how these arrangements do influence the material properties. This is the objective of this chapter 3. Make sense? So going back to this definition again, what does it mean, a periodic pattern? Let us consider this example of crystal here. A pattern, first of all, it should be set of atoms, like 2 or 3 or 5 or 10 or 100 of atoms. They're gonna form a certain shape, and this shape, it will be counted as a pattern. Make sense? So for example, I can choose one pattern, like I can deal with these 4 atoms. They're gonna form this diamond shape, for example. So this is like one pattern. These 4 atoms form a certain pattern. And then I'm gonna consider the next other 4 atoms. They are forming the same pattern. And then we do have another 4 atoms who are forming the same pattern. So this diamond shape, it is a pattern. This shape, it is a pattern that is formed by 4 atoms. Make sense? And then this pattern is repeated over certain period. So what does it mean period? If you choose the center of this pattern and the center of the next pattern, you're gonna find that there is a distance between them, right? And if you choose the center of the next pattern, you're gonna find another distance. But definitely this distance, it should be the same. So we're gonna say that this is repeated pattern, that this pattern will be repeated entirely through the entire material. Like these atoms, they do have a certain arrangement, and every group of atoms, they form a certain pattern, and this pattern is repeated. Repeated, it means periodic. Periodic, repeated with a well-defined arrangement. The condition to be periodic pattern is that these distances should be identical. But for example, if this pattern, you may have the same pattern, but this pattern is randomly distributed. So this will not be counted as periodic pattern. So the condition, so we have 2 parts here. Pattern, it means that you have a group of atoms. This group of atoms gonna form a certain shape. No matter what this shape is, but anyway, this is gonna be counted as a pattern. Then if this pattern, it will be repeated, if this pattern will be repeated in an organized way or not. If it is, if the repetition of this pattern is organized, so it will be counted as periodic pattern. So this means that we may have non-periodic pattern. You may have the same pattern that is repeated, but repeated randomly. So it will be counted as non-periodic pattern. So there are two conditions here. To have a crystalline, to form a crystalline material, it requires two conditions, two things. First, that the atoms, they should be arranged to form pattern. And then the second condition is that this pattern should be organizedly repeated. It should have a specific repetition, identical repetition all the way through the entire material structure. This is what does it mean a crystalline material. So a crystalline material is the one in which atoms are arranged. It is not any type of arrangement. It is a special type of arrangement to be counted or considered as crystalline material. This arrangement, it should be following a periodic pattern over large atomic distance. It is not necessary, by the way, for this periodic pattern to be repeated for the entire material, but at least it should be repeated for a large scale atomic distance inside the material structure to be counted as crystalline material. Make sense? So for example, if you're gonna compare this amorphous structure, can we, for example, find any specific pattern? One single pattern for this amorphous structure or this random distribution? No. For example, I can select these four atoms to form a square. It will be hard for you to find this pattern is repeated. So for example, I can have another pattern. Like these three atoms, they're gonna form a triangular shape. These three atoms, they're gonna form another triangular shape, because as you can see, there is like kind of distance between these two atoms. This distance is not here. So it means that this pattern, despite it should be the same shape, triangular shape, but it is a different pattern. These two patterns, this triangular pattern and this one, it is not identical. So for this random distribution, it will be hard for you to locate a pattern. Even though if you located a pattern within this random thing, if the distribution of this pattern, as we mentioned, it is non-periodic, it is random, also it will not be counted as crystalline material. So there are two conditions, that you should have a pattern, and this pattern it should be repeated all the way through the material. And in the meanwhile, it should be periodic. It means that the distribution of that pattern, it should be organized as already given here. Like for example, I can locate another pattern, which is going to be the same identical pattern, and next to it the same pattern will be repeated. Keep repeating this pattern through this entire material domain. So we're going to say that, okay, this arrangement of atom gives us a crystalline material. So this arrangement, number one, gives a crystalline material, and it will be counted as crystalline material. So generally speaking, all metals, and many of the ceramic materials and a few types of polymers, they may form some crystalline or periodic structures. They may have some periodic structure, so it means that they could be counted as crystalline structures or crystalline material under normal solidification conditions. Here we are talking about the solids. In the solid material, in the normal case, under the ambient conditions, which are at the atmospheric temperature, the atmospheric pressure. So it is in the normal case of these materials, all metals in general, they are crystalline. What does it mean they are crystalline? They do have periodic structures. They do have periodic pattern. Their atoms are well arranged. They do have a specific arrangement to form patterns that repeated equally through the crystal structure. And these patterns are three dimensions. Since we are talking about a material, this material in the three-dimensional case, so it's going to be like, instead of being two dimensions, so what I'm representing here is two-dimensional pattern. But in fact, the material is three-dimensional thing, so this periodic structure, it should be three-dimensional pattern. It means that the repetition of this pattern should be repeated equally over the three-dimensional space. Anyway, forget about this point, but anyway, all metals, they are crystalline materials. Some of the ceramic material, they are crystalline. Many of them, they are crystalline. They form crystals. They can be counted as crystalline solids or materials. But polymers, few of them, most of the polymers, they are amorphous. A few of the polymers material, they can be counted with some crystal structure, or at least they should have some parts in their microstructure that contains crystal. It's going to be clear as we move on through the next slide. So a crystalline material has a specific crystal structure. This is another thing. What is a specific crystal structure? This pattern, when it is repeated, forms a crystal. So we're going to say that this material has a crystal structure. It means that it contains crystal, and this crystal, the atoms inside this crystal, they do have a specific arrangement or distribution, and this word or this keyword will be clear as we move on. Make sense? So what is a crystal structure here? It's the representation of the manner or the way in which atoms, ions, or molecules. We may have material that composed of atoms. We may have a material that composed of ions. We may have another material that is composed of molecules. Ions, if you remember, the ion, there is an atom, but unstable one, or with a charge. The charge, it means that the number of protons is different than the number of electrons, as we explained in chapter 2. Make sense? So, if you do, no matter what is the basic unit that form this material, whatever it is, atom, ion, or molecule, these atoms are arranged in a certain manner, in a certain way. This way of representing or arranging these atoms is known as the crystal structure. So the crystal structure, it is the representation of the manner in which atoms, ions, or molecules of a certain material are arranged. This is what defines a crystal structure. So this means that we may have one material with a certain crystal structure, with a certain way of arranging atom, and we may have another material that whose atoms are arranged differently than this material. So we're going to say this material has a crystal structure that is different than this one. So the crystal structure, it is how you arrange atoms inside the material. If the arrangement of the atoms is different from one material to another material, so we're going to say that these two materials, they do have two different crystal structures. But we may have two different materials, but of the same crystal structure. So again, we may have one material, the same material type, but two different structures. Like we may have aluminum with BCC crystal structure. We may have aluminum with FCC crystal structure, for example. So it means that it's still the same element type, it's still the same atom type, it's still the same material type, but two different structures, two different arrangements of atoms. Also, we may have two different materials like copper and aluminum. We may have copper with FCC crystal structure or BCC crystal structure, and we may have aluminum with BCC crystal structure. It means that we do have two different materials but of the same crystal structure. So the crystal structure is the representation of how we are arranging atoms inside the material. This is what does it mean, the crystal structure. So all crystalline material, they do have a specific crystal structure. Every material has its own crystal structure. That it could be identical, the same crystal structure for another material, that is fine, but it is something that distinguish also, that we can use to distinguish one material from the other material. Make sense? So, in general, crystalline material is a material with a crystal structure. We can say that. We can say that a crystalline material is the one with a crystal structure. But what does it mean, a crystal structure? It is the arrangement of atoms, how we are arranging atoms inside the material. Crystalline materials, these are materials with a crystal structure whose atoms are arranged in a periodic three-dimensional pattern. And we understood what does it mean, periodic pattern, two conditions that should be there. Over a large atomic distance, this is what defines the crystalline material. The other type of material, some of the properties of crystalline solids depend on their crystal structure. There are so many, some of the properties of this crystalline material, they depend on the crystal structure, and this is the objective of this chapter or this course, how the material properties are dependent on the crystal structure, how the material properties dependent on the arrangement of atoms inside the material structure. If we are arranging these atoms in this way, what type of properties do we expect? if we did change it, this atomic structure or this distribution arrangement of atoms, are we going to end up with different properties? Yes, absolutely yes. We do have different properties. So these links, these connections between the crystal structure and the material properties will be explained over this part. The second type of material here is amorphous material. So since we discussed crystalline, it means that atoms should be arranged. It is intuitively to understand that amorphous, it is non-crystalline material. We can give it a name as non-crystalline material. It is amorphous. It means that atoms are random. There is no specific periodic pattern inside the material. So it will be counted as amorphous material. It's the one whose atoms are not arranged, there is no specific arrangement, and instead do not have a long range atomic order. So we're going to talk also about long range atomic order. Like this one, it has long range atomic order. What does it mean? It means that these four atoms form a certain pattern, certain order, certain arrangement. This arrangement will be repeated for long atomic orders. It means that for long, it means that it will be repeated like one, twice, third, fourth, and so on. It will be repeated through the material. But amorphous material, some of the amorphous material, for example, they could include some patterns. They could include the same pattern, but this pattern, it is not repeated identically. As we mentioned, it's going to be a non-periodic pattern, so it will be counted as amorphous material. So amorphous material in general, we can say that amorphous material is the material whose atoms are randomly distributed inside its structure, or in other words, to be more accurate, that whose atoms they don't have arranged, they are not arranged or don't have a long range atomic order or arrangement. This what does it mean, the amorphous material, and what distinguishes the amorphous material from crystalline material. Remember that all metals are crystalline. Some of the ceramics, they are crystalline, some of them are amorphous. Like glass, for example, it is amorphous. Atoms inside the glass structure, it is very random. There is no specific arrangement. There is no periodic structure. There is no crystal structure for glass. Glass, it is a ceramic material, yes, but it is amorphous, not crystalline. Polymers, the majority of polymers are amorphous. Some of them, a few of them, they could have parts of their microstructure could be crystalline, and the other parts will be random. Usually polymers, and I believe that the chemistry engineers who are aware with this thing, polymers, they are made of kinks and links of atoms. Like you do have a chain of atom, and this chain of atom it will be randomly kicked and linked inside the material structure. So it is very random structure. That's why it is amorphous. This is many of the polymer material will be in that way. Make sense? Now we need to discuss the second arrangement, which is polycrystalline. Polycrystalline material is the one whose structure, it means that it should have a specific atomic structure, is a composition of many crystals. So it means that polycrystalline, it comes from the word we mentioned once before. Poly, it means multiple. Crystalline material, it means that this material, it consists of multiple crystals, of multiple crystalline things, of multiple crystalline material. Multiple crystalline material, it means that a polycrystalline material, it is a material with multiple patterns that will be repeated identically, or of multiple periodic patterns. So again, a polycrystalline, just stick to the word itself, polycrystalline. So poly, it means multiple. Crystalline material, we said that any crystalline material should have a periodic three-dimensional pattern. So if we're going to talk about polycrystalline material, it means that it should have multiple periodic three-dimensional patterns. This is what does it mean simply polycrystalline material. So polycrystalline material is the one whose structure is composed of multiple crystals or multiple three-dimensional periodic patterns. The three-dimensional, every single three-dimensional periodic pattern could be used for forming something that we're gonna call as a crystal. So the crystal, it is a composition of atoms, ions, or molecules. The thing that form this material, which are arranged in a periodic three-dimensional patterns over large atomic distances. So going back to this definition, We could say that a crystalline material is the one in which whose atoms, ions, or molecules are arranged in a periodic three-dimensional pattern over large atomic distance. The same definition as crystal. So what does it mean this? A crystal, it is already a crystalline material. One single crystal, it is a crystalline material. It has a certain periodic three-dimensional pattern. But if this three-dimensional, so you may have one crystal with a certain arrangement, with a certain three-dimensional periodic pattern, and you may have another crystal with another three-dimensional periodic pattern, and another crystal that have another three-dimensional periodic pattern. If you combine all of these crystals together, you're gonna form a polycrystalline material of the same type, for example. So it means that the polycrystalline material, it is a material that is made of multiple crystals. And what does it mean, a crystal? This is the periodic three-dimensional pattern of arrangement of atoms inside the material structure over large atomic distances. Make sense? In material science, we usually give name to the crystal as grain. Some people, or the material scientists, they give the name to crystal as grain. We give it a name as grain. So the grain, it is a crystal. You should understand it this way. The grain, it is just a crystal, and this crystal has a specific periodic three-dimensional pattern of atoms. Therefore, we can give a name to polycrystalline material as granular material, which comes from the word, this granular, it had been driven from the grain word. So if you decide to use crystal to say that you have a material of multiple crystals, this means that you have polycrystalline material. If you decided to say that you have a material with multiple grains, so we're gonna say that this material is a granular material. Make sense? So this means that we may have a material of multiple grains, multiple crystals. Can we have a material of one single crystal? Yes, this material, it will be considered as single crystalline material. So we do have polycrystalline material, or we may have single crystalline material. So in general, we could have crystalline materials in general. They could be either just one crystal that form a material, or you may have a material that is composed of multiple crystals at once to form one material. If it is multiple crystal, it's going to be polycrystalline. If it is single crystal, it's going to be single crystalline material. Is the one whose structure is only one crystal, contains only one single crystal. This is a single crystalline material. All right, so to understand it more, let us consider here this polycrystalline material example, this one. So it is polycrystalline, so it means that it should be multiple crystals. So we have to allocate or define these multiple crystals. So, but it is clearly seen in this figure, right? I can, for example, assume that this group of atoms, they are forming one crystal, and this other group of atom, or this cluster of atom, form another crystal, and we do have a third crystal. So we're gonna have multiple crystals. But we cannot count all of them as one single crystal. Why? Because the arrangement here, it has been disturbed, or it changed to the next one, change it to the third one. So every part, or every one of these three groups of atoms, they do have their own atomic arrangement, kind of, or direction or orientation of arrangement. So they form like a one single group, and there is another single group, and there is a third single group. So we're gonna have one crystal, second, third. So there is multiple crystals. So that's why it is classified as polycrystalline. But this one is just one single crystal. All the atoms, they are forming one single group. So it is just one single crystal, or one single crystalline material. It could be counted that. This one is random, as we mentioned. This is amorphous. But let us focus here, something that you should understand about this polycrystalline material. All the crystals, the question is, we do have this group forming a crystal. So this is one crystal. This other group form another crystal. This is a third crystal. The question is the crystal structure different from this one to this one to this one? It could be, or it could be not. Depends on the material. We do have some polycrystalline materials that this crystal will have its own crystal structure. Remember, what is the definition of the crystal structure? It is the representation of the manner in which atoms, ions, molecules form or arranged. So the periodic structure, if you changing the periodic three-dimensional structure, you're already changing the crystal structure. So again, if you change the periodic three-dimensional structure, the crystal structure is going to change, as we mentioned. So, is it fine if we do have this crystal has its own periodic structure, and this crystal has another periodic structure? Yes, that is fine. We do have some of the material that do have this specification. This will be discussed with more detail in chapter, I believe, either 5 or 7. Yeah, chapter 5. Or we may have, but in the conventional case, if we're going to talk about homogeneous polycrystalline material, that its crystals, it has multiple crystals, but all the crystals, there is a common thing between them, that these crystals, they do have the same three-dimensional periodic pattern. Or in other words, they do have, all the crystals, they do have the same crystal structure. The crystal structure is the three-dimensional periodic pattern. So for example, I could choose, for example, for this crystal, this periodic pattern. This periodic pattern has like 3 in each, every 3 atoms form a pattern. So I'm gonna say that this is one pattern, and this pattern, by the way, it should be kind of repeated. Like assume that there should be another, because the drawing is incomplete, so there should be so many. The number, the count of atoms inside the material is in millions, right? We're just representing a few atoms. So it means that there should be another atom here and another atom. So these 3 atoms will form the same period, which will be repeated identically. It means that we do have one crystal. This group form one crystal. This crystal of a certain periodic structure. Then if we decided to move to the other crystal, I can choose, for example, the same pattern here, which is going to be repeated inside the crystal structure. You got my point? So you're going to have another like part of the pattern. It is not necessary that you should have the pattern, it is complete. It could be incomplete. But remember that this is like part or half of that pattern. It means that we still have the pattern, it is repeated. The same thing here. We may have another pattern and so on. There are lots of detail, by the way, of choosing the pattern, but let us assume that we choose this one. So the same pattern, we're still using the same pattern to represent this material, right? And this pattern, it is periodically distributed. It is distributed equally through this crystal and the other crystal. So we're gonna say that we do have 2 crystals. This is one crystal, this is like crystal 1, this is crystal 2. These 2 different crystals, they do have the same periodic structure. They do have the same crystal structure. So we do have 2 crystals of the same crystal structure. The same thing, we can select the same pattern here. But as you can see, this pattern is kind of oriented somehow, but it is still the same. We do have also, we can select the same pattern here, and this pattern will be repeated as already given in that way. So we're gonna have a 3rd crystal of the same crystal structure, but it is a different crystal. So there is a crystal, there is a crystal structure, there is a pattern. The crystal structure is the pattern itself. How we are arranging atoms inside the material, this is the crystal structure. Make sense? The crystal, it is a composition of atoms of the same periodic arrangement, of the same crystal structure. Like all atoms are arranged in a 3-dimensional periodic pattern over the large atomic distance. This is the crystal, and this is what distinguishes polycrystalline material from single crystalline material or amorphous material. As I mentioned, we could have one material that is made of only one single crystal. We may have another material that is made of multiple crystals. It will be counted as polycrystalline material. Make sense? Now we're gonna move to something that we call as unit cell. So remember that so far we're just trying to fix some of the important keywords that we're gonna use through this chapter or through this course. Like unit cell, for example. So a crystal, which remember it is 3-dimensional periodic structure, can be divided into unit cells. This unit cell, it could be counted as the pattern. So for example, if I choose one pattern here, and this pattern will be repeated entirely through this crystal. So this is crystal. This pattern, it can be counted as a unit cell. So the unit cell is like the pattern that it shall be repeated to form this equally to form this crystal. So this is what does it mean, a unit cell? So the unit cell, is the basic structure or the periodic three-dimensional pattern unit or building block of the crystal structure, and it is chosen to represent the symmetry of the crystal structure such that when it is repeated, this is the condition, the overall crystal will be formed or built up. So, like for example, I can count all of this as one crystal. Why one crystal? Because there are atoms, and these atoms are well definedly distributed. There is a specific distribution and arrangement of these atoms inside this crystal. So this huge box or cube of atoms, this entire cube of atoms, it is the crystal itself. I can define within all of these atoms a small box of 5, 6, 7, 8, 9 atoms, a few group of atoms that gonna form a three-dimensional pattern together. And if this pattern it had been repeated, it's gonna form the crystal. What does it mean, a unit cell? So the unit cell, it is the pattern that you choose if in such a way that when it is repeated, it's gonna form the crystal entirely. So we could say that the unit cell, it is the pattern itself that we were discussing before. Make sense? So the unit cell, it is the basic unit cell or the basic unit or building block of the crystal, and it should be chosen based on something that we call the symmetry of the crystal. I won't gonna go deeply through the crystal symmetry things, but it means that this crystal, it should be symmetrical in terms of geometry and in terms of properties. So it is more complicated things, and it is not required to know what does it mean, the symmetry, because it has lots of detail that it should be explained. But for now, the thing that you should understand that the unit cell is the basic structural unit that when it is repeated is gonna form this material. There are rules and concepts based on which we can define these unit cells. But you are not required to know. It is not part of this course. There are lots of detail that should be considered even from physics. So I won't gonna go through these different things. One of these requirements is to achieve symmetry in the crystal structure. And we won't gonna discuss this thing because especially we didn't even discuss the direction and crystallographic direction and orientation and these things. So it will be difficult for you to understand exactly what does it mean, the symmetry of the crystal structure, but you could understand it as like kind of symmetry in the geometry, in the shape. To have this crystal symmetrical in terms of shape, and this unit cell, when it is repeated, is going to form this crystal. This is what does it mean, a unit cell. So for example, if we consider this crystal, I can allocate one cube, one box that contains set of atoms. This box, when it is repeated, is going to form this crystal. This one single box, it will be counted as the unit cell of this crystal. So the unit cell, it is small of atom, group of atoms, certain structure that is going to form the unit cell when it is repeated. There are different ways of representing, and when we study the unit cell and the crystal structure, there are different ways of representing the unit cell. Another thing that you should understand, by the way, about the unit cell is that the properties that we can drive and understand from the unit cell, it is a representative to the entire crystal or the entire material. So again, as I said, the objective through this course, especially this chapter, is to understand how the crystal structure is going to affect the material properties, or the link, what is the link between the material properties and the crystal structure. And we mentioned that the crystal structure is how we are arranging atoms. So how the arrangement of atoms is going to affect the material properties, this is the objective of this chapter. So the question is, how can we study this? Should I study the entire crystal, or that is fine if I choose one single pattern, because this pattern, it is a representative to the entire crystal. So instead of wasting time to study all the atoms, as I said, the number of atoms inside one single, it is millions. So many atoms. So it will be hard for us to study, in order to study how this arrangement of atoms is going to affect the material properties. In order to study this, it will be difficult if you decided to study the entire crystal. Why? The number of atoms is huge. your calculation, there are some of the calculation as it will be shown over the next slides. Some of the calculations that we have to do depend on the count and the number of atoms. So to deal with millions of atoms, it will be very hard. So the other option is just to choose something that represents this huge number of atoms, which is the unit cell. So we could deal with the unit cell as a representative, is a small crystal, is a small structure that if we decided to study and derive the properties of this crystal from which it will be representative of the properties of the entire crystal. So instead of wasting time of studying the properties of the entire crystal, that is fine if you could able to drive and select a unit cell and study the properties of this unit cell. The properties that you're gonna determine or drive from this study of the unit cell will be the same properties of the entire crystal. Make sense? So that is fine even if we could give another name to this unit cell as representative volume element of this crystal. As I said, it would be hard for us to study the properties of the entire crystal because of the huge number of atoms and lots of other things. But that is fine if we can choose one volume, one small piece of this crystal and study it. This volume should be representative to the entire crystal. So this is another way or condition based on which we can choose the crystal or the unit cell or define the unit cell for a certain crystal. So in general, the unit cell, it is the basic structural unit or building block that is representative to the entire crystal, and it will form the entire crystal when it is repeated. Something also that is not written here, but you should understand this thing, that the properties that we can derive from this unit cell are representative, are the same properties of the entire crystal or the entire material. Make sense? So how we can study the unit cell? So as I said, the study, and this is what we're gonna do over the next slide. Over the next slides, we are going to focus over the unit cell. We won't gonna study the entire crystal, as I mentioned. So there are different ways to study this unit cell or represent the unit cell. We could use something that we call as hard sphere model of the unit cell or reduced sphere model. What is the difference? Nothing. In terms of study, in terms of calculation, is nothing. But you could say that this is the typical exact shape of the unit cell. Like if we choose this unit cell, you're gonna find this is half of an atom. So what does it mean, half of an atom? Is it fine if I can choose the button or the unit cell to be like, to cut one atom into half or part of an atom? Yes, we can do this. So the unit cell is something that should be, there are lots of rules, as I mentioned, for choosing the unit cell. You are not required to know these rules. Make sense? So for this case, for example, we do have here half an atom. At this corner, we do have 1/8 of this atom. 1/8 of the atom is located at the corner of this cubic unit cell. We do have 1/8 of an atom. 1/8 of an atom. 1/8 of an atom. Over the face, we do have half of the atom. So this forms the unit cell, and this is how it looks like. Every big objects here, these are pieces and parts of an atom. These are parts of one single atom. So this type of model, if we decided, something also that you should understand is that all of these atoms are tangible, like tangent to each other. Every atom is tangent to, touches the other next atom. Like this atom is tangent to this atom at this point, is tangent to this atom at this point, tangent here, tangent there. The same one, this atom, it should be tangent here, and so on. This is something that you should understand about the exact real structure of the unit cell. How atoms are allocated and defined inside the unit cell. All atoms, in fact, in reality, they are tangent to each other. But it could be a little bit difficult to do some calculation over the geometry and some other calculation that we're supposed to do for driving the properties of this unit cell. So we can model it like small circles at the corners, at the face. Like for example, this 1/8 of an atom will be represented like a sphere at this corner. But you should understand that this is in the exact real shape and structure of this unit cell that this atom, it is not a complete atom. In reality, it is 1/8 of an atom for this unit cell. But for the sake of study, for the sake of simplicity, to make it simple, when we do the calculation, that is fine if you represented this atom like it is a complete atom. But in your calculation, you have to consider it that it is 1/8 of an atom. It is incomplete atom. The same thing, over this face, there should be half an atom. I'm presenting it like a point, like a circle, like a sphere. That is fine, but you should understand that it is half an atom, not a complete atom. The same thing over the atoms over the corners. So all atoms here represented as spheres over the corners, in fact, they are 1/8 of an atom. But other atoms that located over the faces, so they have a cube, any cube should have some corners, vertices, and in the meanwhile it has faces. So based on this unit cell that has been chosen for this crystal, that there should be like an atom or half an atom located over the center, because the center of this atom, it should be located in the middle of that face on the top. At the center of that face, there should be an atom. At the center of that face, there should be an atom. Here should be another atom, another atom, another atom, another atom, or to be more accurate, another half of an atom over every single face of the cube. At the corner, we should have 1/8 of that atom at this corner, but despite that, we are representing them like atoms. So this model is known as reduced sphere model. When we do the calculation, we working over this model to make the calculations clear to us. But this is the exact model, the exact shape of the unit cell, which is known as hard sphere model. This is something also to acknowledge or understand the difference between the hard sphere model and the reduced sphere model of the crystal or the unit cell inside the crystal structure. Make sense? So again, why the unit cell is important? Because the unit cell is a representative. It would be hard to study the entire crystal, but it would be easy if we studied the unit cell, do some calculation, the thing that we're gonna drive will be representative to the entire crystal. So now here, so far over these few slides, we have defined what does it mean crystalline material, polycrystalline material, what does it mean crystal structure, unit cell. These keywords are important to acknowledge and understand them before we move on to any other thing through this chapter. I spent enough time to explain these keywords because they are highly important, because in the next slides, starting the next video, for example, we're gonna talk about the crystal structure and we're gonna mention this keyword all the time. So you should understand what does it mean crystal structure. We're gonna mention unit cell, so you should understand what does it mean a unit cell. So these keywords are important to understand them so we could follow through the next slides or the next part or the other parts of the chapter. So that's it for this video. The next meeting, I'm going to discuss the metallic crystal structure. Why metallic crystal structure? As I mentioned, all metals, they are crystalline. All metals, they are crystalline. Some of ceramics, they are crystalline. So that's why we could drive the thing that we could understand from the crystal structure of metal, it can be applied to any other crystalline material. So since metals in general, all of them, they already crystalline materials. So the focus it will be over the metallic crystal structure through the rest of the chapter. And we're gonna discuss the face center cubic, body center cubic, and hexagonal close packed. These are three different atomic arrangements. These are three different three-dimensional periodic patterns, three different crystal structures. So what are the types of crystal structure? The common type of crystal structures of metals, they are either face-centered cubic, which known as FCC crystal structure, or body-centered cubic, which are known as BCC crystal structure, or hexagonal, which is HCP, hexagonal close-packed crystal structure. This what will be discussed over the next videos. Make sense? And we're gonna distinguish the difference between them in terms of properties, in terms of other quantities. So that's it for this video, and this is the objective of today's lecture. It is just 3 slides, right? But it is important to understand every single one of these keywords that mentioned over these 3 slides, so you could follow over the rest of this chapter. Make sense? So that's it for this video, and thank you so much, and see you in the next lecture.